Okay, this is notes. We are going through L1, question L1. Okay, a student pulls a school bag along a table with a force P. So this is the pulling force. It may not be the F net yet. Okay, let's read on. As shown in the figure below, when the bag is moving, there's a frictional force of 0.5. So there is another horizontal force of 0.5 as well as P, which is a pulling force, and they are in opposite direction. So explain why P must be greater than 0.5 Newton for the bag to accelerate. So this is an application of Newton's second law, okay, whereby it says that there must be a resultant force. So F net must then be equals to P minus 0.5. So therefore, P needs to be greater than 0.5 in order to have F net. Okay. So the answer will be P needs to be greater than 0.5 in order for there to be a resultant force to the right. Okay, and that's still not enough. So with a resultant force, according to Newton's second law, then there will be acceleration. Okay. Okay, part B. The force P and the frictional force in the figure are not a Newton's third law action-reaction pair. Okay, describe the other force that is the part of the action-reaction pair with P and state the body on which it acts. Okay, so in order for it to be Newton's, a pair of Newton's third law action-reaction pair, it has to fulfill these four criteria. Okay, so they must be the same type of forces. Same type of force, and acts on opposite body. So this one will tell us why P and frictional force are not Newton's third law action-reaction pair. Okay, they must be equal in magnitude and opposite in direction. Okay, so this second condition is important for it to be a Newton's third law. So P acts on the bag. P acts on bag. Okay, and P is by student. Okay, so I will say student pulls bag. Newton's third law says that it must act on opposite body, therefore bag pulls student. Okay, with an equal but opposite force. Okay, and this pulling force is of the same type of force. Alright. Okay, next question, L2. It shows that there are two blocks, M and capital M and small letter m, connected by a light string passing over a smooth pulley. So if it's a smooth pulley, that means there is no friction. Alright. When M is released, the small m is released. Okay, the blocks move with constant speed. That means there is friction on the horizontal surface, right? Because by right, if M is released, okay, it's going to fall with due to the pull of gravitational force. Okay, so by right, M should accelerate, because M, in order for it to accelerate, there must be a net force. Okay, so the pulling force is from the pull of the weight of M, small m. So maybe let me just draw this. W small letter m. So there's this W small letter m. This force is pulling on the big block, the block of capital letter M, right? So by right, if this is the only force, then there should be acceleration. However, the blocks actually move with constant speed, meaning there must be a frictional force that is equal and opposite to the weight of small letter m. Okay, so that's why it moves with constant speed. Because when you read constant speed, right, it means that there is no acceleration. No acceleration means no F net. Okay, so for this big block capital letter M, there must be frictional force on the horizontal table, although the pulley has no friction, but on the table there is friction. Okay, so which of the following correctly describes the motion of the blocks immediately after the string is cut? Let's say the string is cut over here, right? Then your small letter M block, it will accelerate. You will move with increasing speed because now there isn't a pulling force upwards, all right, due to the frictional force. Okay, it is now actually just falling with the weight, so it will move with increasing speed. For M, because this capital letter M, the big block, it is cut, so there's no longer a pulling force, right? However, it's still moving on a table that has friction, so it will actually decelerate. So it won't stop moving right after this, because the question asks for immediately. Of course, after some time, after it decelerates, it will stop moving, but they are asking for the keyword immediately. Okay, so it's either A or C, and it will not move with constant speed because remember, there's no longer a pulling force, but there is still a friction force. Okay, so answer is A. Okay, now we go to L3, a box of mass 5 kg. So this is the M. Move at a constant speed. When we read constant speed, somehow it has a 8 meter per second. It means that there is no acceleration, and when there is no acceleration, it means no F net. Okay, so later we will need to draw a free body diagram just to be clearer. Then there's a rough surface. So rough surface, that means there is friction. Okay, so this happens when it's being pulled by a 10 Newton horizontal force. So let me just draw the free body diagram. Let's say it's being pulled with 10 Newton. Okay, so because the question really tells us that there is friction due to the rough surface, so in this case, it is moving with constant velocity, therefore no acceleration, no F net, which is here. Therefore, friction must be equal to 10 Newton. Okay, so this is part A. Now for B, the box now move from the rough surface to a smooth. So for smooth surface, we take it that there is no friction. Okay, assuming that there's no change to the applied horizontal force, state and explain the motion of the box on the smooth surface, 3 marks. So let us draw the free body diagram first. Now the surface is smooth. That means no friction. There is no change to the horizontal force, is still 10 Newton. The mass is 5 kg. So I can actually calculate my F net or infer that F net equals to 10 Newton because that is the only horizontal force. So if I have F net, I'm going to have acceleration. So 10 equals to mass, check that it is 5 kg, check that it's in kg, so that I can get my acceleration of 2 meter per second square. That means it's going to be accelerating at a rate of 2 meter per second square. Okay, so the motion of the box will then be, box will accelerate at a rate of 2 meter per second square. Okay. C, while the box is still moving on a smooth surface, all right, and with the horizontal force remaining constant, which is 10 Newton, a force of 7 Newton is now applied in the opposite direction. Right, state the effect of this on the motion of the box. So again, let us draw the free body diagram. So it was 10 Newton. Okay, I keep it constant, but now there's a force of 7 Newton applied in the opposite direction. Okay, so the free body diagram that you draw won't necessarily be the same as mine, but it should be the same to reflect the conditions in the question, right? Some of you may draw this 10 Newton like that, and then 7 Newton. In the end, it's the same, right? Because a push is actually like a pull, because there are still forces. So with this, I can actually calculate F net again. Okay, remember how to draw FNet? It must be not touching the object and with a double arrow. So FNet equals to, we take the larger number minus a smaller number, we get 3 Newton, right? So my FNet actually decreased from 10 to 3 Newton, right? So what does it mean for the acceleration? Before that, my acceleration was 2 meter per second square. Now my acceleration, let me do a calculation. FNet equals to ma. The mass remains the same, 5, my a. My acceleration is now 0.6 meter per second square. Okay, so they want us to state the effect of this on the motion. So a lot of you may be tempted to say box slows down, right? Because the acceleration decreases, but this is incorrect because there is still acceleration of 0.6. So I'll say that the box velocity is still increasing. It increases at a decreasing rate, at a lower rate, okay, due to a smaller or lesser value of acceleration. Increases at a lower rate than b. Okay, so if I were to draw the VT graph, it will be something like that. Let's say, right, the gradient of a VT graph, it will be gentler and here will be steeper. Okay, so this is my part B and this is my part C.